Okay, so we're going to do a brief review of all things linear equations. Okay, so there are going to be 3 assignments. I'm going to cover the first 2 today, and I'll cover the next one tomorrow, and then I'll give you a day to work on this stuff. But it's all, I mean, the vast majority of this is going to be review. We'll probably extend a couple things maybe further than what you did in Algebra 1. But it's linear stuff, so it's not real complicated. Okay, so and these are the topics we'll hit. We're going to look at standard and slope-intercept forms of linear equations, horizontal and vertical lines. We'll talk about what that means and how we write them. Parallel and perpendicular lines and how we can test to see if lines are parallel or perpendicular or neither. And then finding and using intercepts to graph lines, which is a really handy trick to use in graphing lines. So first of all, what do we mean by a linear relation? Well, a linear relation in 2 variables, x's and y's, let's say, so in 2 dimensions, the graph always looks like what? Straight, but what would we call that? A linear relation has a graph that always looks like a what? No. It's linear. A line. There you go. Yeah. So if we were to plot a bunch of values of x and y, and they would all line up in this linear pattern, and then when we connected those, we get a line, right? So this seems pretty simple, and it is when you're talking about lines in 2 dimensions like that. It gets a little more complicated when you have linear equations with many more variables. Seems a little strange to talk about linear equations with more variables, but we do. In 3 dimensions, what does a linear equation look like? Does anybody know? In 3 dimensions, a linear equation actually produces a plane. In 4 dimensions, a linear equation produces a space, and we could keep going. We can do linear equations with 10 dimensions if we wanted to. That would be very non-physical. Our universe only has 3 extended dimensions, but it's possible other universes have different numbers of extended dimensions. But those linear equations, even if it doesn't seem like they apply geometrically in our universe, they're still really useful. And a lot of what you do in higher math involves dealing with systems of linear equations. In fact, one of the most powerful tools you'll ever learn, if you go on to study mathematics, which I hope you do, is linear algebra, using matrix theory and linear algebra to solve these large linear systems, to represent important things in our universe with systems of linear equations. We use it when we are, for example, if you are designing integrated circuits, like large arrays, very large scale integrations of integrated circuits, then you use a lot of linear algebra. If you in quantum mechanics, the study of the physics of the very small, it pops up all the time. There's lots of linear algebra associated with that. And so it does get more complicated when you get to higher dimensions. But for now, we're just in 2 dimensions, and it's pretty simple. There are several ways of writing linear equations in 2 dimensions. We got 3 different ones we're going to look at. Today, we'll look at 2 of them. One of them is standard form. Anybody remember what the standard form of a linear equation is? It involves A's and B's and C's. AX, say it again? A plus B plus 1. No, it has to have X's and Y's in it. This look familiar? AX plus BY equals C. Okay? Yeah, that's standard form of a linear equation. Why do we write linear equations in that form? Well, that's a useful form for us to use if we're going to be doing lots of manipulation of multiple lines in a system. A lot of times we use matrix math to do that, and the way we'd like to write our linear equations if we're going to use matrix math is in standard form. Okay, and that's a topic for later, but that's one reason why we might write it this way. So what are the rules in standard form? Well, these are not, I'm going to give you the rules, but then I'm going to tell you that they're not really rules. We can break these rules, but when we can, we like to use them. So we like to make A, B, and C integers, if possible. So if they're fractions, if we have 1 or more fractions, we would clear the fractions. But we might have values that are of a, b, or c that are not rational numbers, like pi, for example. That's fine. We could do that, in which case we couldn't write it as a fraction. And so we, or as an integer. We can't always write a, b, and c as integers, but when we can, we like to. What about the next rule? Okay, this is definitely not a rule. Does a have to be positive, greater than or equal to 1? No, it really doesn't. It really does not have to be. A could be negative. And oftentimes in college, when you take your linear algebra classes, a will be negative. It doesn't matter. But sometimes we like to make it positive because it just makes the math a little bit simpler in some instances when we do make it positive. On the homework, they're going to ask you to write some equations in standard form. And I put a little note, like you guys are familiar with, I think it's called the instructor tip. When you go to a question, there will be a little thing that will pop up that will give you a little information. I don't do it very often, but I did it on this assignment. I always reminded you that they expect the answers to have positive values of the leading coefficient, a. So it does need to be positive on this assignment. And then the other one, which is kind of important, is that when we have rational coefficients, we would like the greatest common factor to be 1. We don't want to be able to divide. If we can divide both sides of the equation conveniently by an integer, we'll do that to make the coefficients smaller. Okay? That's it. So let's look at a couple quick examples here. Like what about number 1? If I wanted to put that, is it in standard form? It is. What's the one rule that we're breaking on this one? If we're going to follow these rules, what's the one rule that we're breaking? A needs to be positive. So what's the only thing I would have to do in that equation to follow all the rules? What would I have to do? Switch the signs. How do I accomplish that algebraically? What's the step I would take? Yeah, and I would prefer to multiply. You could divide, but multiplying is easier. Just distribute a -1 on both sides, which just changes the signs of all the terms. So that would just become, if I distribute -1, we just get positive 5x minus 6y equals positive 12, and we're good. Okay, give me thumbs. That makes sense? All right, what about number 5? What would I do? Yeah, clear the fractions. We want integer coefficients, so what would I distribute? 12. Yeah. If I distribute 12, what do I get from the first term? 9x. 12 over 4 is 3 times 3 is 9. Second term. Minus 4y. And on the right side? There you go. Done. Okay? Good? And then finally, what about this guy? What would I do here in number 6? First thing probably. Clear the fractions by multiplying by 6. Okay, multiply by 6. What's that going to give me? 1x, so just x. Okay, and then now what? Subtract 6y, and we're done, right? That's it. X minus 6y equals -12. Okay, put them all in standard form. No big deal. Okay, let's move on to the next form, slope-intercept form. This is the one everybody knows. What is slope-intercept form? There you go. Y equals mx plus b. Very good. Okay. What's the meaning of m?
Slope.
Slope. Yes. What's the meaning of b?
Y-intercept.
The y-intercept. And if we wanted to, we could write that in function notation. Same thing. So let's talk about slope. What's the definition of slope? Okay, how did you guys always describe that in the past? Slope is what? Rise over run. There you go. Slope is rise over run. And what does that mean? If slope is rise over run, so there's two ways to describe that. One way would be to say rise over run is delta y over delta x. What does delta mean in math? Yeah, so usually it represents the words change in. So change in y over change in x. The change in the y coordinate is going to be the rise, because y is the vertical component, right? Change in x is going to be the run. That's the horizontal component. Okay, a lot of times we try to write that with more specific points. We write it using the formula. You've seen this formula, the slope formula. Slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. A lot of times we just don't say sub, we just say y2 minus y1 over x2 minus x1. What does that mean when you attach a subscript to a variable like that? Okay, they're ordered pairs, yeah. So when we have a subscript like that attached to a variable, it doesn't mean a variable anymore. Those represent numbers, not variables, right? Variables are meant to vary. When we include a variable in an equation, like if x is in an equation, x could take on any number in its domain, right? That's the whole point of the x, is it is there to vary, right? We want it to be a variable. When we attach a subscript, no, not anymore. Now these represent specific fixed points that we're going to plug in numbers here to represent these coordinates. We attach the subscript 1 for, call it the first point, and the subscript 2 for the second point. Does it make any difference which is the first and which is the second? No. You just have to make sure you're consistent, right? They're two different points with a different pairs of coordinates, okay? So then we could kind of divide slope up into 4 different categories, say 4 types of slopes. One possibility is the slope is positive. What are the characteristics of a line with positive slope? Okay, so as x increases, y increases, right? In other words, an ant walking in the positive x direction from left to right would be walking uphill. So it would look like something like that, right? There's a line with positive slope. We could have a line with negative slope. What would be the characteristics of a negative slope? Yeah. So as x increases, y decreases. An ant walking in the positive x direction from left to right would be walking downhill. What about the case where the slope is between positive and negative? What if it's 0? Okay, that's going to be, show me with your arm what that one looks like. Yeah, that would be horizontal, wouldn't it? And that makes sense if you think about it, because if I take 2 points on a horizontal line, there is going to be some run on the bottom of the fraction. It's going to be a number, but what's going to be the rise? 0, right? And 0 divided by a number other than 0 is 0, right? So that gives us 0 slope. Okay, what about the case of a vertical line? That's the only case we haven't looked at. If I take 2 points there, the rise is going to be some number, isn't it, between those 2 points? What's the run going to be? 0. Ah, okay, that's a problem, because a run of 0 means we're dividing by 0. Can we do that? No. So what's that tell us about the slope? Yeah, it's undefined. Good. Okay, so then we've got all our slopes. Now what we want to practice next is just writing equations in slope-intercept form, which makes them very easy to graph. This is very simple to do. To write an equation in slope-intercept form, all you do algebraically is isolate y on one side and then simplify. That's it. And that puts it into slope-intercept form. So for example, number 10, what would the steps be to, we're just isolating y, right? That puts it into slope-intercept form. So what would I do to isolate y? Add 1 and that's it, right? Don't I just get then y equals negative 4x plus 1? Agreed? Okay. So what is my slope? Negative 4, and let's write it as a fraction, negative 4 over 1, so it looks like a rise over a run. What is my y-intercept? 1. Yeah. Okay, so then if we want to graph this thing, we're going to graph this line like I graph any line. The strategy is always the same. Let me ask you a question. How many points are required to specify one exact line? If I have a single point, how many lines could pass through that point? An infinite number, right? So that's not enough. Two. All it takes is two distinct points, two different points. If I have two distinct points, two different points, it could be in 2 dimensions, like on a graph, a Cartesian plane, or it could be in 3 dimensions in our universe as we know it. It doesn't matter. If I have 2 points, there's only one line that can possibly pass through both of those 2 points at the same time. That's it. 2 points defines a line. So that really gives us our strategy for graphing a line. Anytime we want to graph a line, all we have to do is find 2 points, because that defines that line, and then just connect and extend. How am I going to go about doing that if this is the information that I have? The slope is -4/1 and the y-intercept is 1. Where would I start? At 1, because that's a point, isn't it? The y-intercept is a point. So I would go up here to y equals 1, or 1 on the y-axis. That's my y-intercept of 1. And now how am I going to do this? How am I going to use this slope to create a second point? Okay, good. I'm going to use a slope triangle, right? A slope triangle is a triangle it's a right triangle that's always built from the rise and the run of a slope. If a slope is negative, we have to attach the negative sign to either the top or the bottom. Where would we always choose to attach it? To the top, right? The bottom, the run, or the denominator of any slope fraction is always positive. So that tells us when we're creating a slope diagram or a slope triangle, the triangle is always going to run to the right. But a positive rise would mean I'm rising upward. A negative rise would mean I'm rising downward, right? So then if the rise over run is -4/1, what am I going to do? Yeah, I'm going to do the vertical part first. I'm going to rise by -4 and I'm going to run by +1. So I go to the right by 1. And I create a second point right there, and then all I have to do is just connect and extend. There it is. There's my line. Okay, easy, right? Create 2 points, connect and extend. Slope, or the y-intercept, is always going to give me my first point. A slope triangle gives me my second when I'm graphing lines in slope-intercept form. Okay, let's take a second and let's talk about horizontal and vertical lines, because those are weird ones to name. The equations are strange. If I draw a vertical line and I just look at some representative points, what do you notice is common among all those points? The x-intercept. I mean, not the x-intercept, the x-coordinate, right? The x-coordinate is the same. Does it matter what the y-coordinate is? No, the y-coordinate could be anything. That line extends forever, right? Okay, so if a vertical line really only depends on its x-coordinate, the math gods are very wise. They would not include a y in the equation then, because it's insensitive to y. It doesn't matter what y is. It only matters what x is. So what do you think the equation of this red line is then? That's it. X equals -3. The x-coordinate is the only thing that's important in graphing a vertical line. Okay? What about a horizontal line? Yeah, the y-coordinate is going to be the same for every point on a horizontal line. The x-coordinate could be anything. The line goes forever. So again, the wise math gods, they don't need an x in that equation. They just name it based on the constant y-coordinates, the common or the shared y-coordinates, which in this case would be 1. Okay? Give me thumbs on that. Does that all make sense? Okay. All right, how about parallel versus perpendicular? See what you remember about this. Parallel is easy. We'll warm up with parallel. If 2 lines are parallel, how are their slopes related? They have to have the same slope or they would cross at some point, wouldn't they? Right? So yeah, the parallel lines have equal slopes. This is the tricky one. What about perpendicular lines? They intersect at a right angle, but what can you tell me about their slopes? So one has to be positive and one has to be negative. That's for sure, right? If two lines are going to be perpendicular, if one of the lines is increasing, the other one would have to be decreasing, right? True, but there's more to it than that.
Opposites.
Well, opposites means they have different signs. That's true, they're opposites. What else, though? There's another part of that.
They have coefficients.
Let's look at an example. So if we just make them opposite, look what happens here. Okay, there's two lines, y equals 10x plus 3 and y equals negative 10x minus 1. Okay, well, those are opposites, but that's not enough. Those are clearly not perpendicular. Oh, whoops. Okay. The red one has a slope of 10, blue one has a slope of negative 10. Clearly not perpendicular. What else do I need to do? True, but really we don't care about the y-intercept. Y-intercept is irrelevant. Let's make this one like 2/3, how about? And let's make this one negative 2/3. Oops, that's negative, negative is positive. There we go. Okay, again, close but not perpendicular. Think about that. Think about the road map an ant is taking to walk on the red line. He's going to rise 2 for every 3 that he runs. If I want to do something that's perpendicular to that, yeah, it's going to be an opposite reciprocal. What if I do, aha, look at that. Those are perpendicular, aren't they? So they have to be opposites, so one line increases while the other line decreases, and the slopes need to also be reciprocals to be at 90. Okay? Is that ringing a bell? Remember doing that? Vaguely? Okay. So we know then slopes of perpendicular lines are always opposite reciprocals. Have to be both. Opposite signs and the fractions need to be flipped. So let's look at a couple quick examples here. What about number 15? I've got the left, the two lines. What about the first line? The equation on the left, what would I have to do? How would I know? How would I test to see if these lines are parallel or perpendicular or neither? What would I do? Plug them into what? Well, we don't have Desmos on the test. What are you going to do?
Plug them into the original slope of each equation.
Oh, okay. If I knew the slopes, I'd be set, wouldn't I? Because we know that in order for lines to be parallel, the slopes would have to be equal.
Yeah.
For them to be perpendicular, they would have to be opposite reciprocals. Okay, how am I going to find the slope? What do you mean solve it? There you go. How about that? We could isolate y because isolating y puts these into slope-intercept form. Y equals mx plus b. And the slope would end up just being the coefficient of x on the other side when I simplify it, right? That's a great way to do it. So put it into slope-intercept by isolating y, and then just by inspecting the equation to see what the coefficient of x is, we can determine the slope of each line. Okay, let's try that. So negative 8x plus 8y equals 0. What are the steps to get y by itself? Add 8x. And then what? Divide by 8, and I get y equals x. So what's my slope? 1, because the coefficient of x is 1 there, right? Okay, so m is 1. What about the other line? What would I do? Subtract x, then what? Divide or multiply by negative 1 to change all the signs. And so I'd get positive y equals x minus 4. So what's my slope there? Yeah, my slope is 1, so they are parallel. Because the slopes are equal, we know they're parallel. Okay? How about this next one? I don't know what number it is, but First equation, what do I do just to isolate y? Subtract 9x, then what? Well, I mean, I could, but I'm just trying to get y by itself. So what would I? Divide by -6. Okay, so now let's look at that. If I divide by -6, let's look at that math real quick. -6y equals -9x minus 20. Okay, we're going to divide each side by -6. But that gives me a common denominator on the right. I don't really want a common denominator, do I? I want to split those fractions up, which is no big deal. How do I split fractions? I just make two different fractions, right? I divide each term by -6. So I end up getting y by itself equals -9x over -6 plus -20 over -6. Okay, well, whatever I get that's being multiplied by x, the coefficient of x, is going to be my slope. So what's my slope going to be? Okay, well, that reduces to 3/2. Yeah, so I get the equation y equals 3/2 x plus, who cares? Because all I care about is the slope, right? I'm just trying to determine if these lines are parallel or perpendicular or neither. So there's my slope. What about the other side? What would I do? What's the only thing I have to do here? Divide by -3. That's going to give me y by itself. What am I going to get on the other side? -2/3 x plus, who cares? Right? I know that my slope for the other line is right there. So what can you tell me about those two lines? They are perpendicular because they are opposite reciprocals. Okay, one more. How about number 13? What would I do on the left side? Okay, is that going to work? Let's see. Yeah, let's do that. Okay, so we subtract 10x, so I get 5y equals -10x plus 5. Next step. Okay, that gives me y equals what? -2x plus, who cares? 1, but not that we really care, right? That's my slope. How about this other line? What do I do? Subtract 16. I'm going to flip them around so the y's on the left side. So I get -x minus 16. Everybody agree? And then divide by 2. And I get y, let's do it in red. Y equals negative what? 1/2 x minus 8. So what can you tell me?
Perpendicular.
Perpendicular?
They're opposite.
They're both negative. Yeah, okay. So parallel, perpendicular, or neither? Neither. There you go. Neither. Okay. We're getting there. Quickly. What's the equation of that line? X equals or y equals? The slope is 0. Show me with your arm what that looks like. So is a horizontal line named by its y coordinates or its x coordinates? Y. It has all the same y coordinates. The easiest one to think of is the y-intercept. In this case, the easiest one to identify is that guy, right? So it's just y equals -5. Why is it y equals? Because it's horizontal, right? Okay, that line is in slope-intercept form. What's the slope? Zero. Right? How do you know it's zero? Well, what's the coefficient of x in that equation? If there's no x, what must x be multiplied by? Coefficient 0. There you go. So the slope is 0. Okay. How about that one? Show me with your arm what that looks like. Okay. What coordinates are all the same?
X.
X. So it must be an x equals, right? X equals what?
-4.
There it is. Piece of cake. All right, last issue for today. I'm going to turn you loose. X and Y intercepts. So you guys all know what X and Y intercepts are. We all know that an x-intercept is a place where a line, or it doesn't have to be a line. For now, we're talking about lines. So a place where a line intersects the x-axis, crosses the x-axis. Y-intercept is where the line crosses the y-axis. So what are the coordinates of the x-intercept? -3, 0. You bet. Because we know that it has to have coordinates. I guess it doesn't do that. It has to have coordinates, a y-coordinate of 0 to be on the x-axis, doesn't it? Right? To be on the x-axis means, what does it mean? What do the coordinates of an ordered pair really represent? They're just giving us a road map from the origin. How would an ant get to that location, right? How the x-coordinate tells us how far the ant's going to move horizontally. The y-coordinate tells us how far the ant moves vertically to get from the origin to some point. Well, if it's on the x-axis, the ant can't move vertically at all, so the y-coordinate has to be 0, right? Makes sense. What are the coordinates of the y-intercept? 0, +4. Good, and we know the x-coordinate would need to be 0. Okay. All right, so this is not important, honestly. We'll come back and talk more about this later. There's different ways. X-intercepts, depending on the context, could be referred to as a root, a 0, or a solution. 0 is kind of important. That one will come up soon. Well, why do you think an x-intercept could be referred to as a 0 of a function? The x-intercept is where what is equal to 0? Y. Yeah. Okay. X-intercept is where y is equal to 0. Isn't y the same thing as f of x? So the value of the function is 0 at the zeros, or the x-intercepts, the places where the function crosses the x-axis. Does that make sense? Okay, so those values of x are the zeros of a function. So this one, its 0 would be -3, because that's the input value where the output is equal to 0. That's the meaning of the word 0. Okay, we'll get back to that later. All right, last issue. Really good little trick here. So we know that x-intercepts always occur where the y-coordinate is 0, right? So if I have some equation, can anybody think of a really sneaky shortcut for finding the value of the x-intercept? Yeah, right? We're just trying to ask the math gods, what's the x value when y is 0, correct? Isn't that what we're doing? That's the meaning of the x-intercept. Well, how do we ask the math gods that question? What's the value of y when, or value of x when y is equal to 0? Well, we just set y equal to 0 and the math gods answer us with an equation. So there it is. Set y equal to 0 and solve for x. Fair enough. If I want the x-intercept, I'm setting y equal to 0, correct? This is a great little trick. It's called the cover-up technique or cover-up method. You're just going to set y equal to 0 and solve in your head for x. What are the 2 steps to solve for x? So what do you get? -25. Done. Easy, right? Whoops. Okay, well now, what would my corresponding strategy be for finding the y-intercept? Set x to 0 and solve for y. We can do that. Set x to 0, and that's pretty easy. What's y equal to?
50.
There you go. Right, set x to 0, and y is 50, okay? And the math you guys did in your head is, you don't, that's it, but it is math, simple math, solving two-step equations that you can just do in your head. Okay, so let's try a quick example, and I'll turn you loose and let you guys work on this. So I want to find the x and y intercepts in order to graph this equation, because what's always our strategy for graphing a line? 2 points, connect and extend. Well, why not make those 2 points the x-intercept and the y-intercept, because they're so easy to find? Okay, let's find the x-intercept. What do I do? Okay, good. I'm going to set y to 0. And solve for x. Fair enough? What's x? 15. So 0, 15, that's out, what do you think, right about there? Okay. Good enough. What do you think it was, 14.9? Okay, that's, yeah. Question?
Should it be 15, 0?
I mean, 15, 0, you're right. Yep, whoops. Thank you. $15, 0, good. Okay, what about finding the y-intercept? What would I do?
X to 0.
Set x equal to 0. There you go. And solve. Okay, well that just means covering up the x term and solving. What's the answer? -6. So 0, -6 is right there, and then all I have to do is just connect and extend. And there's my line. How about that? Good? Okay, you can go to work. There are 2 assignments up there. Have at it.